area of a triangle is half times the product of its base and its height. Yep, we're in a typical math classroom setting, and the teacher has just presented a formula, and I'll go on to explain a few examples of its use, delving into applications of how it can be used in the real world. But wait a second, how do we get to that formula? The teacher might present a bit of a cursory proof about the formula, but that only leaves a few more questions. How do we come up with that? What are the motivations for that? So in most classrooms, we don't really get that sort of an understanding, and so we're left to think about math as just a series of formulas and algorithms that we just really have to know and memorize. But what if we just doodled around for a second? We might think about maybe inscribing a triangle inside a rectangle. This doesn't really have any purpose. The triangle doesn't really represent anything, and neither does the rectangle. We're just really playing around. But if we draw a line between them, found the altitude of a triangle, and then we'll see that each of the two rectangles are actually split up exactly in two by the diagonal lines in the triangle. And so the area inside the triangle is exactly the same as the area outside. So we get the same formula, but we get a deeper understanding of exactly how we got to it. So in my presentation, I'm going to focus on three topics. One, that there are two ways to teach mathematics. Second, that it's actually best to split them up. And the third topic is about two different systems, a system of splitting up mathematics that has been used in many Commonwealth countries and several graduate programs at universities, which splits them into pure math and applied math. And I'm going to go and evaluate that system, showing that it's really good, but there are several ways that it can be improved. So, in my introductory example, which was taken from a paper on mathematics reform by a mathematician named Paul Lockhart, you see that there are two distinct ways to teach mathematics. The first one, where we went through the formula and explained how we can get through its applications, focuses on how it can be applied to topics like science, engineering, and economics, where knowing exactly how formulas can be used is extremely useful, more than actually understanding exactly how we got to them. The other form of teaching mathematics is just teaching mathematics for the sake of mathematics, where mathematics is it's more of an exploration of mathematics than actually for any particular purpose. So the first one is more useful in that it has many applications into the real world and into several different vocations, but it's less stimulating for students that are actually interested in mathematics. And on the other hand, the other form of mathematics is a lot more stimulating, as it leads to a lot more exploration, but it's less useful, as it takes the distance from actual applications is much more removed. I'm just going to denote these two types of mathematics as one as a tool for science and the other as an inherent art. So clearly both of these are very useful for teaching, but they're kind of distinct. But we want to make use of both of them. So ideally, what we're looking for is something in between. We were trying to find a balance between teaching mathematics as a tool for science and as a tool for art, and as an inherent art. However, in an interview I conducted with a teaching assistant at Stanford named Yuri Boriku, he made a very interesting comment where he said that while it's possible to find a balance between the two, it's actually very difficult for most teachers to do it. He said that while he's seen a few teachers that can do it, he's admitted that he struggles a lot with doing it himself. And he suggests that it actually is not an effective implementation. So, in other words, it's actually best to split them up. So instead of thinking about it as this, we should really be splitting apart the circles and thinking about it like this. So, while there is an intersection between teaching it as a tool for science and teaching it as an inherent art, we should really be considering how to teach them separately, because teaching them in the same classroom really limits the kind of utility you can get from teaching mathematics. So one possible one possible implementation of this, which has been done before, is with teaching it as applied math and pure math. Applied math is the version of teaching math as a tool for science, and pure math is teaching it as an applied art. So since these aren't exactly the same thing as the two forms of mathematics that I explained before, I'm just going to give a basic overview of what that is. So in teaching it in applied math, you would essentially go through things like graphs and tables and how those would be used to understand mathematical concepts. You also teach to think about applications to physics, quantum mechanics, and how we can use mathematics in those contexts to enact effective applications. It's also been used to take in various applications in computing. Actually, this is where some pure math ideas that were used before have now become very useful in the applied math area. For instance, ideas in number theory have recently been used in very, very useful methods in cryptography. In fact, most encoding schemes use the fact that it's very hard to factor integers, which is something that's a very common thing to teach in pure math. So that's how pure math can also affect applied math. But pure math, on the other hand, can go into more abstract ideas, like this is an example of Fermat's last theorem, a very popular math problem. Which basically explores very different ideas. And while there's really not that many applications of this to be used in the real world, it's still very interesting to think about. Another example is just ideas about abstract ideas about numbers. So it's another example of just tootling around. You can come around and come up with a triangle named Pascal's triangle, where the sum of any number is just basically the sum of the two numbers above. So in pure math, you just basically come up with these kinds of ideas. Applied math usually uses them in some sort of concrete example and context. Another common example of what's the difference between pure math and applied math is golden ratio. So on the right, we have the golden spiral, which is basically a spiral based on the Fibonacci numbers, which are shown over there. But these have many actual examples in nature. For instance, this is a mollusk of a seashell or whatever. So that basically demonstrates how that is used in the real world. And in fact, in many biological areas, the Fibonacci series is actually used a lot in like the patterns that are shown in flowers, for instance. So we see that the pure math and applied math distinction is very well perceived in this sort of a setting as well. So this distinction has been used, as I said, in a lot of education systems in the Commonwealth countries and in graduate programs in many schools around the US as well. So while it's been useful in that setting, it isn't easy to transfer it to other settings. So that's where we see that the system of applied math and pure math is very good, and it gets the kind of idea across, but it's not exactly perfect. So first, I'm just going to go through a couple, not all of them, but a couple of the shortcomings of this idea and how they can be possibly remedied. The first is that the division between pure math and applied math is made very late in a student's education. So in high schools across some Commonwealth countries, you see that the division will be made only for one class in Form 6 or grade 11 or grade 12. So that is very late, and it doesn't allow, and so basically, especially in pure math, it makes students jump right into the pure math without having a basic foundation of mathematical ideas at a very abstract level. So that is a clear shortcoming, but the distinction made before, the problem with what it was before is that it caters to students on that high level. And so while students are being introduced to pure math at this late stage, they don't understand how it can be used they don't have the proper background to be able to actually apply it. And the second issue is that pure math in many academic settings still focuses on memorization of things like proofs or algorithms to solve proofs. And that still detracts from the creativity that pure math is really meant to stimulate. So, in conclusion, we have these three ideas. That there are two ways to teach mathematics, but in fact, instead of finding a balance between the two, it's best to split them up. And while the system of applied math and pure math is good, it's not perfect. And by finding a proper separation, where we can actually both stimulate students and get them to understand the basic concepts needed for vocations, I think that you could really achieve a very good idea of how to teach mathematics in education. Thank you.
Thank you, Prithvi.